Yeah, hello. Well, for me in Germany, it's still good morning. I can say good afternoon to you. And thank you that you made it to my speech. And I would like to say, everybody in Malaysia, yeah, thank you for the nice welcome here. And I really like the country. And I'm proud to be here at HITB in 2005. So make this one big. So everybody in the back, can you please dim down the light a little bit? I can hardly see my in Bamberg, Bavaria, in Germany, and I have a thesis project in refactoring security anti-pattern and distributed Java components. Yeah, but that's not for living. For living, I have to earn some money, and I do security management at a large financial group in Germany. So we do Java and J2E. Corba, design and development, security hardening, and code audit. And there's a nice intersection between these two topics, which I will present in the following slides. So we have to deal with Java everywhere. Java is on the platform, it's J2SE, Java 2 standard environment, but most of the aspects we will see in the demo at the end will also apply to J2E. And Java is designed as a programming language with many inherent security features, like written by Gong and Oaks in the large books. And on the JVM level, you have type safety, bytecode integrity checks. On the API, you have the security manager, the class loader, and the third path for the certificates. And for role-based access, you have Java authorization and authentication services. And for crypto people, they have the JCE, JCA, and the Java secure sockets. So we shouldn't be exposed to any dangers. We are in a safe environment. So what's the problem? Why do I give this speech here? So there have been there have been some Java security alerts in 2003 until 2005. And there has been a large history of it, like already presented here at HITB from LSD. But the history has continued, and there are now new Java versions out, but these new Java versions also have their security alerts. So applets are still allowed to escalate privileges, and they are still crashing JVMs, still denial of service. And embedded products or browsers, they have their integration problems with Java. So some browsers allow access to some packages, and some ports of Java have their own problems, like the port of Java on Mac. So there's a lot of attack potential despite of these precautions in the Java security architecture. And on the next slide, we will go into the reasons and what is behind these problems. So a Java problem, a Java platform, like any other runtime environment, is designed by humans, so it contains errors. The humans are the programmers, and a programmer sometimes on a Monday morning maybe does bad programming, but not the topic here. He may be interested in functionality as application programmer, communication patterns, marshalling frameworks like ARMI, Corba, or XML. And the security architect, like seen before, uses crypto object and secure sockets to secure the insecure applications designed by the application programmer. And there are always the people who want to break systems with malicious intent, and these are the people, the adversaries, who try to undermine security by finding the one weak spot. And the Java VM and the core libraries, they have a couple of them. So this is the architecture, the security architecture of the class loaders and the protection domain. You see there are privileged classes, the privileged classes which are loaded from the bootstrap class loader and from the extension class loader. They have a parent relationship, and they are on the top. And on the bottom you see the application classes, which are bound in a jail defined by the policy, which is, for example, defined by the applet sandbox or by the application server policy. So an attacker sometimes seeks or often seeks the way into the privileged classes to trick these classes into control paths he wants them to use. There are some security bugs not only in your own code, there are bugs in middleware components. You reuse these middleware components in a lot of trusted places, and these are sometimes already loaded by the boot class loaders, where they're very privileged, and can we really trust them? I don't think we can, because they're not really audited for security purposes. So your graphics library may have vulnerable code, which can be triggered by an attacker, or your desktop JVM isn't really secure in isolating your banking confidential data from other malicious applets loaded into the same JVM. Or if your data is transferred via object serialization, so it may be altered, it may be somehow manipulated, so it crashes or it manipulates a remote JVM and does not do what you want to do as a programmer. So Java is not alone on the desktop. Java has found its way from the toast machine to all the other tiers in the enterprise. So it's on the client, it's on the presentation tier, it's on the enterprise tier, and of course it's on the back end. On the client you have the standalone version, standalone client, which talks via ARM directly to the enterprise container, or via HTTP, like the browser client, to the web container. And the web container and the enterprise container, they talk via JDBC to the database, or the enterprise container may also access some legacy application via J2C somewhere else in the enterprise. So these are, you see the exposure to the user. On the left side you see the applets, then the presentation tier with the JSP and the servlets. On the enterprise tier you have the session beans, the entity beans, and message-driven beans, and on the back end you have the enterprise adapter, enterprise resources, Java stored procedures, and UDFs. So looks like a nice picture, but what can happen? So you have different kinds of attacks, and the denial of service or the malicious serialized data attacks, which can go via data serialization, via object input streams into remote JVMs, or you just fake a client and do functionality on the client side, which is not allowed by the official client, but you fake or you recompile and recompose some application so it works like you want and not like the application deployed by someone else. But Sun, as the vendor of Java, has thought about it all, and they designed some secure code guidelines. You see from the last update from February 2, 2000, they did not do many work on this topic since then, but at least they give you these 11 guidelines: careful usage of privileged code, what they didn't do, careful handling of static fields, what they didn't do, reduce scope, what they didn't do, careful select your public methods and fields, appropriate package code protection, use immutable objects, never return a reference to sensible data, never store user-supplied data directly, so careful serialization, carefully use native methods, carefully clear sensitive information, which sounds like a normal common sense behavior, but you find a lot of bugs in the JDK due to violation of these code guidelines. So secure unaware coding creates vulnerabilities. Yes, sometimes. Typical Java secure anti-patterns. So the reverse of the patterns. It's like ignoring these security patterns, like ignoring language characteristics. So trick into integer overflows or do careless serialization, expose everything on the wire, or careless use of privileged code. So every code runs with all permissions. Inappropriate field and method visibility leads to covered channels, or covered channels may result from non-final static fields which are shared by different applications on the same JVM. Anti-patterns are hide in your own code. That's what you can change, where you can really redesign your code, but they're also what's very difficult in the libraries you use, and there you have to wait for an update, which is sometimes several years away. So due to academic interest, we audited parts of the JDK 124X and present the findings on the following slides. But how did we do it? How did we automate it? Source code detectors, or source code is very useful, but source code is not what's running on your machine, and often in closed sourced environments you don't have the source code. Decompilers, yeah, they give you a transformation of the bytecode to a readable source basis, but they really don't show what's going on bytecode level. So we choose the bytecode audit analyzers, find bugs, and find bugs we wrote our own detectors with a visitor pattern, and the find bugs framework is based on quality, how to check software for quality, but we extended some detectors for security purposes. And you can put Java programs in a test bed and find out what permission it needs, but for really search for security bugs, we went into the RT-jar and went into the code which is deployed by Sun Microsystems. So that's what we said. It's an open source framework, the findbugs framework, and it's based on BCAL, has a visitor pattern approach, and has a GUI and a command line. But what's most important, it is extensible and allows you to write your own detectors which run through the bytecode, which run through the code which is actually executed. So, and what kind of anti-patterns can we categorize? So we selected a couple of them. So these anti-patterns, bugs and flaws, they are in the trusted code, so like the RT-jar. RT-jar, everybody knows the RT-jar of Java. It's the runtime.jar, which really it encloses all the runtime classes that are exposed as the API, like the Java.classes, but also internal classes like the Sun.classes. So we identified 3 clusters of bugs: availability bugs, integrity bugs, and secrecy bugs. And the availability bug was, for example, triggered by integer bugs or serialization side effects. Integrity bugs were triggered by privileged code side effects, inappropriate scope, or covered channels. And secrecy bugs, there were, for example, exposed to insecure component reuse, like the integration or the insecure integration of the Orc Apache classes by Sun Microsystems, so it was allowed to sniff private XML data between applets. And so we wrote a binary audit toolset to detect these anti-patterns in own and third-party components to be able to fix the vulnerabilities, or at least be aware where they are. So the integer overflow, so this is not an alien or something, this is the integer value range. And according to Blacksim in Frag 60, integer overflows are a serious problem in C and C++. But as Java is, a lot of Java design is stolen from C and C++, these bugs are also in Java. All Java's integers are bound in the range of -f, -7f, and +7f, following not reported to the user. There's no JVM flag set, so an integer can flow over very silently. This is a common pattern also, or common problem in C. The code of JDK 14101 was based on the false assumption that Java integers are unbounded, which led to range problem or integer overflow problem in the Java util zip package. So if you take these parameters or this method signature and see that the small array, which an x offset, which is then added to an integer max value minus y, causes an integer overflow and causes an access on a very high index in this very small array. And this happens in the native routine. So the native routine update bytes somewhere goes to illegal memory access, and consequently the JVM crashes and crashes your whole Java application server, for example. So this is the same again. This is very interesting because this bug pattern is really a pattern, and they did it a couple of times in the JVM. So like in the Adler class or deflator class or CRC class, deflator class, checked output stream and input stream, and on the BD class, they all had the same problem and were fixed in a subsequent release. But the coders at Sun Microsystems introduced these bugs. So what did they do to refactor the problem? They had this comparison, and you see by the off plus len, you have an integer overflow, and then they rearranged. This is what you see on the red line, and on the green side you see what they changed on the following release. So they just rearranged the comparison and got rid of the overflow. So sometimes it's very easy to avoid denial of service bugs. And as a pattern, they could rearrange all the comparisons in the vulnerable classes which were presented here. So this is a quite antique bug, but for completeness sake, we present it here. So this is what's happening in bytecode. So you have these two values put on the stack, iload2 and iload3, which are the local variables put on the stack by the signature, by the calling routine. And then you iadd, and then you load aload1, and then you do array length, and then you compare them, and there the integer overflow already has happened. And what they did on the refactoring, the compiler, of course, produced a sub operation and rearranges some of the bytecode opcodes. But you can find it with in your own code by not using it source code. You can the iadd opcodes or the ladd or whatever. There are some opcodes which add values on the stack. So if you use check for user supplied stack data in local variables, they are put by iload1 or iload2, depends on the stack height, and then you perform a range check, and then you check if there's a native method called afterwards, like invoke virtual or invoke static. that takes the same data. So it's all the data in Java, it's very local, so you can really put it on the local variable and check it. It's not very difficult. So this can be implemented by a findbugs bytecode detector and run on a jar file, for example. Then you get candidates, and with the candidates you can then go into detailed analysis. Of course, you get what's the conclusion of this anti-pattern? The JVM still does not provide an overflow flag like a normal x86, which was designed in 1978, so there's no way to detect those integer overflow conditions during runtime, except by own coding. The Java JVM and Java 1.5 or 5.0 or Tiger, it does not really improve this shortcoming. So you still, as a programmer, have to check for integer overflow in your own code, but if you have a copy of FRAC 60, it may help you in finding these things. Or just write a detector and redesign your code. So this was the first anti-pattern, so we go into the second. The second is about serialization side effects. The normal way to create a Java object is with a new instruction, or the new bytecode instruction, or the opcode, which calls directly into the constructor or the init method of a class. But there are also hidden constructors, the Java serialization API, which is part of the Java I/O package, allows to bypass constructors and create new instances of a class by simply sending byte arrays to a Java I/O input stream, object input stream. And this object input stream, it can be bound to a socket, to a file, to a servlet, whatever, and directly allows you to insert objects into a JVM and cause some dangerous conditions. So they are used by, already said, like ARM-I or ARM-I over IOP or Genie or other frameworks which shift objects through the entire world. So the risk extent, reading serialized objects may force your JVM to branch into complex or vulnerable code regions that are called in the read object method of a class, and the read object method may linger in your own code, the JDK class, or any third-party component or library you use. So if you have your object input stream bound to an external source, an attacker may prepare special handcrafted data packets with serialized binary data. For example, if he sends you an object Java util regex pattern, it can trigger your JVM to compile to become unresponsive, and it may compile forever for regex pattern and regex pattern you didn't even expect. Or it may crash your system, or it may eat a lot of heap space, or it may crash due to other conditions, like in the Java reflex proxy. If you send it a packet with a number of interface names, a certain number, it crashes your system. All despite of the type safety of Java. First, the read object method is if you see the control flow in the bytecode, first the read object is always executed and then it's casted to the object you expect. So you can send an object input stream every type of object you want it to receive, and as an attacker this may come from a vulnerable class. So a vulnerability, this is what Sun said to it, a vulnerability in the Java runtime environment involving object serialization could be exploited remotely to cause the JVM to become unresponsive, which is denial of service. So the issue can affect the JVM if an application runs and accepts serialized data from an untrusted source. So if you receive serialized data from an untrusted source, maybe you should wrap some mechanism around it with checksums or whatever. Or if you see the control flow in the bytecode, first the read object is always executed and then it's casted to the object you expect. So you can send an object input stream every type of object you want it to receive, and as an attacker this may come from a vulnerable class. So a vulnerability, this is what Sun said to it, a vulnerability in the Java runtime environment involving object serialization could be exploited remotely to cause the JVM to become unresponsive, which is denial of service. So the issue can affect the JVM if an application runs and accepts serialized data from an untrusted source. So if you receive serialized data from an untrusted source, maybe you should wrap some mechanism around it with checksums or whatever, or with public-private key to not really accept every untrusted data and put it directly in the JVM, which can cause the effects described here. So, for example, in the Java util regex pattern, what did they do? They accepted what I sent them on the socket or with my special prepared byte package and directly compiled the regex, and they have a bug in the regex class which compiles for eternal time if you give it enough groups. So you send this package, I can show it here. Whoops, I have this package, for example, here. And this is a serialized data, this is a serialized Java object. And it always starts with this magic here, aced 05, and then it has here the class name, and here the serialized UID, and then comes the serialized data items, for example the flags and the pattern is itself an object and it's a string, and if you send it such a string, it compiles, for example, forever, and you send it via remote, via socket, or inject it through a file, the JVM becomes unresponsive. So what did they do in the following release, in the 1.4.2.06? They did lazy compile and they only use the regex from the point on where it's really used in the class and not where it's sent via the read object, or not where it's read directly in the read object method. But they did not fix the bug that it compiles forever, so they did not really fix it completely. So, of course, you can change for read object in the bytecode and search for after the read object in the read object method. Check for algorithmic complexity, which can be heuristically, for example, checked by checking the length of a method, or check for endless loops, or does the read object control flow lead to vulnerable native code, or does it propagate its payload? And this can also be found by the bytecode detectors you can code with the findbugs framework. So the read object method is designed primarily for accepting and checking serialized data, so don't expose this data to untrusted input. And what Sun did, try to defer complex operations from the time of creation to the time of first usage. And it's not the only space where this problem can occur. It can also occur in the externalizable interface. So we have the same considerations with the read external method and the externalizable interface. So this was the second anti-pattern. Now we go to the privileged code side effects. And the privileged code side effects has to do with the new security manager concept that was introduced with Java 1.2, and it has the meaning of protection domains and privileged code, and a request for access if granted, if the code and its principles by each protection domain are granted the permission. So which basically means an access right is only granted when all methods which are on the stack are in a protection domain that have the particular permission, which graphically looks this way. And you see here for example, here you have an untrusted access, and you want to read a file, and or you want to create a temp file, and you have no privileged code paths which are allowed to do it. So this part, the security manager finds out that this is untrusted, and the grant is, or the permission is not granted. In contrast to that, you have here the access controller, the Java access controller, which does a do privileged, and which cuts down the algorithm, the stack walk algorithm to this point and does a do privileged. And the access control checks end here, and therefore this code here, or this stack configuration, is allowed to create a temp file. So you have a lot of these blocks in the JDK, and when you tweak the control flow with parameters in such blocks, you may end up in privileged code paths which are allowed, which, for example, have all permissions and may do things an application is normally not allowed to do. So an attacker may misuse this condition to escalate privilege and escape a limited protection domain, such JNLP or an applet sandbox. And he knows the privileged part, the privileged code blocks in the JDK, and the privileged code blocks which may be defined in the application. And in the luring attack, he tries to trick do control into privileged code blocks and force that block to use parts of injected payload. For example, he may escape the applet sandbox and test for existence of files on the client machine with the Java AVT font ICC profile class, or he may transport temporary files such as executables to the client's machine, which can be launched later, which was described in full disclosure. And he can also fill up as fun the free remaining space of a file system, or an applet can do it with fill up the hard drive with a lot of zeros, and sometimes the system becomes unresponsive, which is also possible. So Yelma extended my Java findings with an IE exploit and used the techniques which was or the vulnerability which was in the Java AVT font with an IE vulnerability, and executed it directly with in the IE, and undermined IE security due to the Java facility of transporting files to the client system. And these, for example, the temp files, and the temp files, they have predictable names, and the JavaScript he used scanned for the predictable names and executed the file in a trusted zone. So most of the described bugs, except ICC profile, are still on the JDK. So unfortunately, no refactoring is available. What they really do in the ICC profile, they added some checks, and the checks then they ended up that not. Let's describe this in another way. The existence of file could be determined by analyzing the exception that was thrown to the user, and what Sun did in JDK 14209. They throw the same exception in all cases, so that was their refactoring in that particular case. But all the other bugs, they are still on the JDK, so you can still use them. So, of course, you can find these two privileged blocks also in the JDK, and find them with detectors. So, let's speed up a bit and do privileged blocks you've seen as a powerful but also dangerous construct to tweak protection domains. But if Sun uses privileged code blocks, they should be bug-free. So if I use Java on my desktop, it should be secure and not filled up with bugs which undermine security. And as a developer, third-party components sometimes used to privilege blocks and go to all permission protection domains, and some code in own code as short as possible to limit the danger potential, and of course detained, like in every case, detained users supply data before propagating it to privileged code, which is also common sense. Yeah, inappropriate scope, as a rule of thumb, Sun says to you that you should reduce the scope of methods and fields as much as possible, check whether package private members should be made private or whether product members should be made private, to really only give the smallest attack surface that's possible. But you should really do that when you design trusted JDK extensions, such as the Java framework, Java Media Framework, and the Java Media Framework really violated the things, but they were coded by Sun. And we will see in the next slides what happened there. So an attacker can exploit the trusted protection domain or permissions of a Java extension. The JVM, the JMF, it's deployed to the extension path or the extension directory of the JVM or the JDK installation, and it had therefore the all permission protection domains, and it accesses system memory via native routines, and the public JMF class blah 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 .nba exposes a public pointer to physical memory, which directly maps via long value data to the memory available to the Java process. So untrusted applets were allowed to read system memory and send it somewhere home. So this was also fixed in Java Media Framework 2.1.1e, and 2.1.1c was still vulnerable. So vulnerability in the Java Media Framework may potentially allow an untrusted applet to exit unexpectedly the JVM or gain unauthorized privilege, and the unauthorized privilege were reading system memory. So what did they do in 1.1c, 2.1.1c? They made all this data public, and by subclassing the NBA class, you were able to play around with the native memory and map it to your own Java structures and then manipulate physical memory. And the refactoring they did was first declare the NBA class as final, so you are not anymore allowed to subclass a class, and they put all the sensible data into private fields, and the private fields, then you were not anymore able to access them. And with the protected declaration of finalize by the findbugs framework, you search for inappropriate public declarations, and you can check these public declarations and combine their occurrence with native code, which is with the example of the Java Media Framework. So inappropriate scope may allow to bypass access control mechanisms, and like Sun says, refrain from using public variables. Instead, use accessor methods with calls of centralized security checks, which may, at least in this case, would have helped to overcome this problem. So then we go to AP5, which is goes into the problem of non-final static fields. Static fields are variables that are bound to a class definition and not bound to an object instance. Therefore, they only occur once in the address space of a JVM, and They are what other people described as a singleton pattern. They are only maybe misused as a cover channel, and a cover channel is a channel which is normally intended, or which is a channel which transfers data which is normally not intended by the security policy and violates the security policy. And we show in the following slides that the careless use of static variables allows malicious code to exploit these covered channels between protection domains. For example, you have two applets, and these two applets are loaded into the same JVM. For example, you may use these public variables to transfer serialized data between these applets, which is typically not in the permission set of applets that they can communicate with each other. So they should run in isolated address spaces, but here typically these cover channel definitions allow applets to really work as tag teams, work together to break security protections. So unsigned applets jump out of sandbox, which was in 2003. And what Sun did by incorporating these org Apache classes, they refactored all the definitions to final. In the first variable they already did it, but not for security's sake. They wanted to protect their product name. Therefore they made it final and left the others only static. But from that problem they learned that it should be final also, because it will never be changed and should not be exposed to the user address space to be misused as cover channel. Therefore the final modifier prohibits modification of a variable after initial value was set, and allows you, therefore modification is not allowed anymore after first initial value set. So this can be also found out by find bugs detectors, and you check for public static but not final fields, and check then in your code if it's used in reduced protection domains. And not only primitive data types and strings can be misused, you should also check arrays and containers, because the final keyword does not really affect the entries in these container types. It only affects the definition of the container itself. So an array index 0 is not really final, even if the array is declared as final, which happens a lot in the core definitions of the JDK. So there are a lot of bugs still inside the JDK action between supposedly independent subsystems, which means that data may leak between systems which are intended to be isolated, but your data then travels between the systems and you don't have an idea where data may travel in your JVM. So the last anti-pattern, it's the insecure component reuse. We already had a small example of it, but there's also another example. As a provider of a large of the Java runtime system, Sun was overwhelmed by the functionality of the XML libraries of Apache, so they introduced it into the JDK, but they did not check these libraries for security purposes. So if one weak spot is found in the XML parsing classes, it also affects the the protection model of the overall JDK. So the XSLT parser, for example, which is embedded in the JDK, is directly taken from a previous Xalan standalone version, which is downloadable from XML Apache org. It is complete, it is highly configurable, and it allows you to customize the functions that may be employed during the XSLT. XSLT is extensible style sheet language transformation, and therefore non-final static arrays in the trusted libraries contain objects that are allowed to process data throughout the entire JVM space because they are allowed by the Bootstrap class loader. And then these classes are in an elevated protection domain and therefore may do things other things are not allowed to do. For example, it introduces a class which is allowed to modify data in these packages to insert malicious callbacks. And these callbacks, for example, allow untrusted applets to read data from another applet that is processing XSLT and may allow the untrusted applet to escalate the privileges. It is allowed according to the sandbox, which may be very dangerous, for example, in a banking application, and the one applet uses XSLT transformation for some stuff, and another applet introduces a callback, and then the untrusted applet gets all your data, which is transformed by the XSLT, which is not really a good idea. So what did they do in 14205? They had this public function, and the public function could be used to define your own this function table, and the function table, it had objects in it which defined your own, which could define own parsing functions, but which is not really allowed in a limited protection domain. So they modified it to private in 14206. In 14206, they adjusted the public table to a private table, and therefore it was not allowed anymore to manipulate the function table of the XSLT parser, and therefore it was not allowed anymore to sniff the data which was transformed by a wrap-off or a combination of the other cases we have seen before. Can include integer overflow, or you check for integer overflow, you check for improper serialization, and you check if you use really only privileged code when it's executed in the all permission protection model. It's not a good idea to have large parts of privileged code. If you adjust your fields to a appropriate scope, you may be safer than before. And if you add security checks to public variables and fields, it may also help you to enforce a security policy. And when you use static non-final fields and static mutable container types, it may also end up in covered channels. So these are the sorts you should be aware of when you introduce third-party components, which may all introduce these problems into your system. So even if your own code is secure, your third-party components may ruin your security concept. So if your vendor of the components you reuse, sometimes, or better, ask them for if they checked their components with find bugs or similar tools, or if you have a closed source vendor, you may ask them a couple of times and then they become aware that you are really interested in secure use of their component and not only in a functional use. A lot of open source projects already include a find bugs report, but as already said, the closed source guys still have to learn from it. So this was the presentation, and after the presentation we do the Q&A, but first let me show you, for example, how the vulnerable object implementation in the JDK may undermine the security concept, for example, of the JBoss application server. Starting routine with, for example, the JDK 14208. And you see it starts here, and the JDK 14208, it has some vulnerable classes. And if I say, for example, invoker upload, and we look at the invoker upload function, the invoker upload method has here, it just invokes servlet and sends a packet to this URL of the JBoss application server, the JMX invoker servlet, for example, and send it this vulnerable object, for example, the ICC profile there, which is a font description. And if you send it this font description, which you see again is here a serialized object again with this magic number and the SR and the name of the object class, and then here some stuff comes, and I fussed it with some brute forcing, some combination which really harms the JDK. So I sent this manipulated object to the JDK, to the JBoss instance via the servlet upload, and when I send it here, it crashes the application server, because the application server does not, or the JDK under the application server does not check whether this is a valid object or not. So you see it crashes here in this library, and this allows you to do a denial of service attack even on well-coded application like the JBoss application server. How did I say well-coded? Let's say here, the JBoss application server also has these problems. For example, if you say to the web space, and for example, if you say here, get server XML, you get from the JBoss server the server XML via this particular port, which is not really in the sense of the RFC. So also the JBoss application has some problems. And the last thing I want to show you is about use to trigger database operations. And if I send this JDBC request to an JBoss server, it creates a temporary table, it inserts a fake value, and then redefines some properties in the underlying JDK, sets some debug value, sets this property or defines a alias for property, then sends the internal Java compiler to cmd.exe, and then creates an alias for the compile which uses exe, previously it used the java c.exe, and I redefined it to cmd.exe. Then I sent it this command, which triggers, for example, the notepad, or it can be used to trigger a netcat or something else. And then the purpose is here, for example, to trick the JBoss application server into code execution set, which is introduced by these vulnerabilities in the org Apache packages, which allows you to override the internal variables in the JDK. And I have here this AND script, and this AND script simply connects to the HTTP SQL database, which is bound on port 1701, and takes this SQL file and executes it. Of course, it needs some binding information from the HSQLDB. So, long speech, short effect. Then we say here and execute it. And now my etc. hosts is shown just by manipulating the internal variables of the JDK, which is lying under the JBoss server. There you see that may undermine your application safety very severe. So these have been the things I want to show you, and there may be questions you want to ask me, and now it's time for it. Yeah? If you inject this SQL into a JBoss server, for example, it can be used to run executables in the with the writes of the JBoss server. So you need to know the internal variables of the JDK. You need to know which kind of JDK level uses these variable names. For example, in JDK 1.5, these have been changed slightly, but with some 1 hour search you find the new names, or just at sun and try it. These are the names then in JDK 1.5. So this is also exploitable via SQL injection. Yeah, other questions? Yeah? Well, what you really need, is a BCL, the bytecode engineering library, which was coded by some smart guy from the University of Berlin. And he wrote this BCL library, and this BCL libraries allow you to traverse through code, traverse through a class file, traverse into methods, traverse into fields, and then get candidates. And what the Findbugs framework did was define categories and define way to present these things, and defined a common way to automate it. But the BCL does also all the hard work. And you can also do it with, you can write it yourself, but why not use predefined components? Yeah?
The exploit that you mentioned,
Yeah.
which are those that is runnable on 1.5?
Which is runnable on 1.5. For example, there's one which is not published, or which is not, I can show you here. Let me first definition, and you send it with this one, or in hex 1 and 5 JBoss, for example, running, or any Java application accepting remote input. So we start now with Java 1.505, which is quite new, and we send it this package. Oh, this is still running here. Kill this one. connection is broken, yeah. So, and here we see this proxy server, proxy serialized. So all this, see what it's doing here. So this crashes JBoss or any virtual machine 1.5. So this is not fixed yet. So any other questions, or are you waiting for the party? Everybody's waiting for beer. So I don't want to. I don't want. Yes, thanks for your attention. And if you have questions, you can also ask me on the party. But now I first have to drink something, and then we can talk again. Thanks.